All right, thanks again. So this talk is going to be about, at least the first part, is going to be about deriving this formula. So we found that we motivated the formula from the calculation in 1 + 1 dimensions. We found an example in 2 + 1 dimensions which gives this formula. And now we want to derive it purely from 1 + 1 dimensions. So let's consider, again, our favorite setup, just the eternal black hole. And let me review the way of preparing this black hole, which I discussed in my first lecture, which was, I think, like 3 months ago or something. OK. So the idea is that this state can be prepared by the following path integral, Euclidean path integral, where in some part of the Euclidean spacetime, you're integrating over just CFT on a flat space. But then there's a region here where you turn on gravity. That's where JT theory is turned on. And you can think of the entire Euclidean theory, and that looks something like this. So JT is only turned on here, and everywhere else is CFT on flat space. This path integral is defined with some boundary conditions along the circle. For example, that the dilaton has some value, and the metric is asymptotically ADS2. So this is the usual thing. Now, say we want to compute the entropy of a region in the path, which I will call B. The union of the two is B. I'm representing the region with a cut, which is a standard thing one does in computing the entropy using the replica trick. So the thing that we're trying to compute is trace rho of B to the n, then take the derivative with respect to n, and then take n to 1.
Sorry, what was the round picture? The above one I sort of understand.
This one?
Yeah. This was the picture in which you prepared the state on the time slice.
Yes. And here, this is just, so without the cuts. Exactly. I'm just, this is the entire Euclidean plane.
Okay.
So it's like whatever the overlap of the state is just 1 or something.
The distance is irregular.
So
You're not placing it exactly.
Yeah, I mean, I'm not placing it exactly there. Exactly. I'm not placing it there. OK, the way you compute this is you consider the replica manifold. So we have, if we're computing trace rho to the n, we have n such sheets, and they're identified across these cuts. OK, you go in here, you come out there, you go in here, you come out there, and so on and so forth. And now, the idea is that because gravity is dynamical inside these disks, you should allow for all possible configurations, and especially saddles. One particular saddle is the case where each disk is independently filled with just hyperbolic space, so just ADS2 on each disk. And if you work on the branched cover, that just looks something like this. So I've collapsed all these into a single sheet, and you go to the other sheets by going through this cut. And here I just have ADS2. Okay? The claim is that if you evaluate this contribution to trace rho to the n, you will simply get the standard answer, the same answer had this JT region not existed. Okay? So as in, it could be just CFT on flat space everywhere. Okay? That's the semi-classical answer. That's how I'm going to define semi-classical. But obviously, this is gravity.
Even in your ADS, you didn't have bulk CFT. You had some matter.
No, he has matter.
GT plus CFT.
Right. So when you said ADS, you meant ADS with the matter.
Yes, that's right.
Okay.
What I mean,
Take on.
what I'm saying is that the matter will have the multi-sheeted boundary condition, but otherwise each sheet is just filled out with gravity,
Yes.
and then what you'll recover is the log result for the matter.
Precisely. But you know.
You get the answer you would have got had the metric been frozen to be ADS in that thing, right?
That's right. And I think that would be the same answer had it also been flat space.
Had it also been flat space, that
Yes.
completely true.
Okay.
Right.
So I.
From that
having to do with this weird defect inside. So it would compute the entropy of that state, frozen ADS state.
The matter
Here-
is
here's-
conformal,
Yeah,
doesn't see the conformal factor, and so, you know.
exactly.
So discontinuity doesn't matter.
All I'm saying, so remember we had these W coordinates here everywhere? Then, we did a coordinate transformation to consider the fact that we have ADS here. But in computing the entropy of this region and this region, that didn't care about what the transformation was from W to X. It only cared about W to Y. So it should really be the same answer. Okay, and I think there's a way of deriving that from the path integral. Okay, but thou shalt not restrain gravity. Unless you're an ADS.
Could another way of saying that be that if you're doing a wild transformation in the internal region, that's some unitary transformation, so it should change.
Yeah, that's a nice argument, yeah.
If you have a CFT, let's say giving a flat space, and now you have a, let's say, a hole where you have attached a cylinder, so everything is conformally flat. And the observer here in the CFT, the cylinder is invisible. It's like nothing is there.
Depends what you do to this. Do you
State will see what that.
I don't have an answer. I'm not sure. But it's clear from the Lorentzian calculation that we did before.
Yeah.
I was just going to say, so if you just had some Y factor which was varying, and you were computing the entanglement for some conformal matter, you wouldn't really see that Y factor. We just have this log formula, and the only subtlety is the cutoff in this language or that or something like that, but it wouldn't really. I think that's what.
Just at least for the entanglement.
Yeah. Yeah, trace root there. Okay.
Okay.
But actually, mode by mode, I mean, you would just solve for the fields.
Mhm.
Okay, but that's some Minkowski street.
Mhm. The point here is that ultimately you'll get the standard Hawking answer for the entropy of this region. So this was at t equals 0. You can continue to Lorentzian time and evolve forwards, and you'll find the contribution which grows for all time. Okay, so that's one possible configuration or contribution to this path integral. But you can also have wormholes. And so on. So that's another possible configuration, and in fact, a possible saddle.
And can you just describe what this picture means? So the
Yeah.
metric
So let's think about the ADS, the n equals 2 case.
Mhm.
So now we have these two guys. And we have a hyperbolic metric on this manifold, and on this wormhole. And you need to solve, I guess, for the dilaton. That's one way to say it.
Can you draw one more sheet? Just one more.
Want me to draw one more sheet?
With the
Why are you doing this to me?
I don't quite see.
So
I'll give it.
Before you rub it off, sorry. So you just mean by that what was this circle region filled out?
Yes.
Now gets filled out by this trumpet-like thing,
Yes. Two-headed trumpet.
two-headed trumpet. So it has two boundaries now.
Yes.
Are these the same saddle points that appear in Schenker?
Good. So in Schenker and Stanford, they don't find a saddle point.
Yeah, that's
So they have to integrate over the entire modulus being the size of the throat or the radius of the trumpet. But in this case, because we have matter, the matter stress tensor stabilizes it. And it stabilizes it in just the right way to ultimately give us the extremization prescription. Yeah. So the picture is that. Okay? And obviously, in these discussions, you say, well, gravity can give me any configuration. In particular, it can give me one that does not respect the replica symmetry. But it's an assumption that we make that we only allow replica symmetric configurations. Okay? This is standard in these deriving the holographic entropy in ADS-CFT and so on. Okay.
And then how do you decide between these two?
So these are two contributions, and so I'll get there in a second.
What are the relative magnitudes of the action for these two?
That's so.
Is it
As n goes to 1, these are they're all e to the minus 1 over g Newton. Okay, but as n goes to 1, I'm going to write that down in a second. It's e to the minus 1 over g Newton times the generalized entropy. So you have these different contributions, and this is what enforces the minimality constraint. That as n goes to infinity, or as g Newton goes to 0, the one with the smallest generalized entropy wins. Okay, so this is what this thing looks like. But you can work on the branched cover.
So these are almost lessons in Euclidean signature.
Yes.
But what I meant was that the minimality condition is an added assumption, or
No.
Follows,
It follows because.
Can you just
Okay, let me write it down.
because that's the lowest action, then I suppose in the Gn going to 0.
Yeah. So this thing ultimately, I'm going to write down a more careful equation in a second, but this is going to look something like n minus 1 s gen no wormhole. That's what 0 means, plus e to the minus n minus 1 s gen a single wormhole with 2 and 3 and so on and so forth. Now each one of these guys goes as 1 over g Newton. So take g Newton to 0, and you take the leading one. That's how it works. So
N to 1, N to 1, right?
yeah.
That is in type 5 with G Newton, N to 0. Maybe.
No, you're supposed to take the derivative with respect to n first, and then take n goes to 1. So when you take the derivative, that puts the entropy down. Then when you take n goes to 1, this exponential factor goes away.
I'm sorry, the second is an exponential within the exponential, right? There's an e to the.
Sorry,
The
Oh.
second.
this one? Why is there an exponential there? Sorry.
Is it in the exponent or not?
No, these are separate saddles.
Is it? Yeah.
So then don't you have these?
The whole path integral is now.
So it's just a sum of, it's one exponential plus another.
Yeah, that's a plus.
Okay.
Plus an
You think
exponent.
of a gas of instant terms,
Mm.
right? There isn't the
There's in the
boundaries.
boundaries, yeah. It's not the Schenker problem with multiple.
Yeah. Ultimately, yeah. Okay. So this is what you should get. Now let me motivate this. So this is again in the replica manifold in the branched cover. You can represent these wormholes by a branch cut here. Okay. But for n far away from 1, so integer and large, the geometry here, or the dilettante solution, is not the same dilettante solution as in the case for n equals 1.
Sorry, what do you mean you can represent wormholes by a branch cut?
I just mean that let me draw what the branch cut is, what I mean by the branch cut in this case. So this line here is this line. So these 2 points are this point and the point in the back over there. Doing this is like doing this.
It's going from one sheet to the other.
Precisely. Yes. Right. So the thing that I'm
From the usual type of thing, right?
That's right. So this is it's just a point that in gravity you don't actually have a branch point. It's not a singular point. It's a smooth thing in this way. And what I'm drawing there essentially is just sort of one of these guys, right?
Sorry, is this the picture that you get if you take the usual branch cut and somehow stretch it and remove the conical axis? It's a
Um,
topologically different thing.
no, I think it's a slightly different thing. Yeah, it's a different thing. But now the point is that we can work near n equals 1. Okay? So if you work near n equals 1, then the solution is just going to be the n equals 1 solution. So the dilettante solution here and the background and everything is identical to what we had in the case without any branch cuts. So it looks like this geometry that we had. But it's that same geometry, but now with branch cuts. So it's like this now looks like we are computing the, yeah, let me say it and then write the equation. This looks like we're just computing the entanglement entropy of these three subregions on the original background geometry. Okay.
This is roughly the island. This is the one.
Yeah. So the island is dynamically generated by gravity. That's the point. So when you evaluate this,
So the branch cut is an nth order branch cut.
yes,
Is that right?
yes,
So when you take n going to
1,
sorry, n minus 1th order branch. Sorry, what?
it's
I'm
an
confused.
it's an nth order branch cut.
Okay, so when you take n going to 1, I see.
Yeah.
But in Stanford Center's picture, if you had matter, then you expect these quantities to contribute. These wormholes will exist and then they will contribute. Let's say you are calculating.
Yes, I mean that's what I'm saying here.
Okay. As long as you have, so it's the same once you have matter.
Oh, sorry, you're saying if I add matter to this Stanford-Schenker discussion, is that what you're saying?
Yes, and then let's say you have two boundaries.
Yes.
And you want to calculate the path integral. Then these quantities will.
Yeah, yes, I mean, they considered wormholes, but for them, their wormholes were not saddle points. So they had to integrate over the modulus being the size of the the throat, the radius of the wormhole, the radius of the throat. But for us, because we have matter, that stabilizes that modulus.
Indrani is saying if you repeated Schenker and Stanford for a free energy with multiple boundaries, in a theory where you had extra matter, would you stabilize their wormholes now and then get contribution?
Yes, because it's the same calculation.
And you are supposed to have already done that calculation. That's perfect.
Yeah,
Don't
okay.
assign.
So the statement now,
When you now go ahead and identify this picture with the replicatory calculation, the entropy, but of this extended region, that would be true if this cut were of the standard replica cut, right? But
Yes.
now you just said this is a funny cut.
no, but near n equals 1, it looks just like a standard replica cut. That's the point. So if you evaluate this thing near n equals 1, for let's say for this saddle,
But you have something extra on the boundaries of that island. No?
what do you mean?
In the standard two cuts, the ones that you had,
Yeah.
they are different from the one that is in the middle by saying that you need to pick up some delay terms.
Yeah. That's the thing I'm going to write down here. So you need to evaluate the full path integral. You're evaluating it on a saddle of the gravitational part, right? So that ultimately, that part will give you something like this. N minus 1, the dilettante for G Newton on, let's call this region I, on the boundary of I. So this is just usual Lobkowitz-Maldacena. So you literally get this. Then you also have a trace rho CFT to the n on the background metric Gn, so the solution. And but this, I guess it's not explicit here, but this is the density matrix with these cuts, these three cuts. And so when you compute, and so then you can represent this as, in the limit n goes to 1, as just the following thing.
How do you get 5 over 4 GN from the JT action?
Yeah, it just comes out. It just comes out.
Is that right?
Yeah, yeah.
Is it because in effect there's a curvature, sort of thing, conical?
Oh yes,
curvature
yes,
at that
yes, yes,
point?
yes, yes, yes. Exactly.
Cosmic
That's
string.
what.
Yeah, that's precisely it.
Okay.
It's just the usual story. You have some sort of a conical excess or deficit. I forget which one
Okay.
at these 2 points.
Okay.
And yeah, the equations, the bulk equations of motion. Actually, no, that's something else. Yeah, there's a boundary term that comes from the equations of motion that gives you the value of the dilaton here and here.
In that sense, it's not so different from what you were saying, that in the end, going to one limit, at least you're adding a little, smoothing out the conical deficit.
Yeah.
You know, and just sort of, gravity will just smooth it out.
Yeah. And yeah, so in this picture, you have from these 3 cuts, you get as von Neumann entropy of B union I. And from the branch points in the gravity region, you get the dilaton. Okay? So it really just comes out very simply.
If you are calculating matrix element instead of trace, then you have started with two boundaries, two boundaries on the 2 cuts for the bar, and so your matrix element has the basis states are labeled by fields on those boundaries. And how does the middle part is like? Is it always going to get traced or the middle one? It's
Yeah.
just this, but not with the trace, but two states.
Yeah, I don't know what the I haven't thought much about it, so I don't feel comfortable writing equations or possible equations for that question.
Because your 2 sides do not have those fields around this new part.
So if you ask the question again.
Instead of calculating trace, just put 1 state on the left, 1 state on the right. But the states are labeled by cuts due to the bar, actual bar, not the middle one. So,
You want to compute this thing?
there is the one problem. Probably then you automatically always.
So you're not taking the trace means that you have left the top end open and the bottom end open.
Yeah.
And you glue stuff in that.
I mean, this is really very beautiful. So the island really is a reflection in the end, going to one limit of the fact that dynamically gravity will generate wormholes between the various replica
That's right.
sheets.
That's right. But yes, although now I wanted to, okay, something I wanted to emphasize that it's not really about the wormholes, as in it's really just a fact. So there are other situations, which I'm going to discuss in a second, where you don't have wormholes. But the thing that gives you the right answer in computing entropy is simply that the different JT theories can talk to one another. Wormholes are a specific thing about this example. Okay, and in fact, wormholes always contribute. This might be a bit cryptic when I say it right now, but they contribute whenever these cuts are far away from the gravity region, as in they don't touch these boundaries. Okay, so when the cuts are outside over here, then you'll have wormholes. No, actually, even in those parts you can have wormholes. Okay, let me give you the other examples. So first of all this fine?
So as
Okay.
you take that point closer and closer to this circle, you just get to some finite. That doesn't, the
So-
island doesn't extend all the way.
I'll talk about that case. So yeah, so let me talk about that case actually next.
This one question, something elementary.
Yes.
So when you say that, when you take these points closer and closer
To
to
the-
the JT theory, because this is an asymptotically flat case. There's no natural length scale associated with it. So when you say you're taking it close, that's compared to the ADS length scale or some length scale within the gravitational theory.
Yes,
Is that?
you can say it like that. Okay, let's consider the case where the branch cuts really hit the ADS boundary. And by hit the ADS boundary, I mean they go slightly inside. Okay. The same thing, trace row to the n. So if let's draw two. Let's look at the n equals 2 case. Let's think of the Schwarzian particle. Okay? Schwarzian particle. So let's say, it's very close to this boundary. Let's say we go in this direction. The Schwarzian particle is going to come out here, right? Let's go along this way. Over here, it's going to come out there. So by joining the cuts over here, we now actually have a circle for the Schwarzian particle. As in the right picture to draw, I guess is what I'm saying, is the following. Let me draw this thing again. So what actually happens is that each sheet attaches to the one below it. That makes sense? So the thing that's happening is that this gravity, so in some sense, this half of the gravity region is attaching to this half of the gravity region on the other sheet. So that's this picture, that this half is attaching to this half. That can be represented as this. Right? So this entire half here gets connected to this half. So this half is this half, this bottom half is this top half. So you just have a product now of sheets. They're not connected. They don't talk to each other.
That the particle comes back after n time?
No.
So
immediately.
Adjacent sheets, they factorize the particles move only in
Between subsequent sheets.
See, why is that? Why doesn't it have to go n times?
It's because of these cuts. So it's because these cuts they end here at the ADS2 region. So.
But normally, if I just look away from the boundary of the JT, just for matter, if I go from the top and come to the bottom of the first cut, I show up at the top of the second. It's true. Then when I go around the second, I come at the top of the third.
But I'm not going around, right? So just usual just cut. So we're doing this, right? We're how should I draw this?
In complex analysis, this cut can be replaced by the cut in the middle.
Yeah.
In complex analysis,
It has to do with the fact that you have dynamical gravity in between there.
No.
Otherwise,
in the middle, we can take
okay, without, sorry, I see, but without gravity, it wouldn't be the case, right? If you take the n-replicated manifold, it's not that you just end up factorizing between adjacent.
Oh. I mean, I didn't tell you. I didn't tell you what the gravity solution inside here was. First, I was just tracking the location of the boundary particle. And I was noticing that on subsequent sheets or consecutive sheets, the Schwarzian particle gets located entirely in these two consecutive sheets.
Confused by the Schwarzian particle word. If I just had the CFT without dynamical gravity and I drew some branch cut
Like this,
that,
let's say.
Yeah.
Okay.
Then of course I would only come back after going through the end sheets.
No, but that's no. So Exactly. So if you do this,
Oh, if you go around both of them.
yes, which is what the Schwarzschild particle is doing.
But that
So you go
would
down and then
be-
you come back up.
Okay.
is what is
I
the statement.
see, I see.
Sounds like CFT chop the whole thing. Then you go from this to that.
Exactly. But gravity is the thing that allowed us to chop it. As in, there's a gravitational solution where the filling of this disk happens on sort of consecutive sheets. As in, the first and the second, the first half of the first and the second half of the second, and the first half of the second and the second half of the third, and so on and so forth, in this way.
It's related to the fact that you have two cuts. If you had just, let's say if you want to calculate for only right path, but you want to use this gravity prescription, then would you say the same? It should not factorize, right?
It should not. It should not. But we'll get there in a second. I'll compute that in a second.
That's sort of what I was thinking, that it won't factorize, but somehow. But I mean, there's a, if you just did it for the pure matter CFT without any dynamical gravity, also you would have this periodicity.
Yeah, but it would
just
not
because you're going
factorize.
both around, but that doesn't mean.
Yes, exactly.
factorize,
And
right?
Exactly.
that's the origin of this formula, that the gravitational part factorizes, the dilaton comes out, but this trace rho to the n CFT, which is just the whole of CFT without gravity using the usual replica trick.
Yeah,
Is
that's
that the correct interpretation of?
yes. But the idea is that without gravity, these different sheets do not get. It doesn't factorize in this way, but what gravity does is that it joins. So gravity, again, it fills in the branch cut here, is I guess the statement. Right? So you had first the branch cut, which I guess I can draw the circle. You first had just these branch points, but gravity creates a branch cut here. And that's this picture that these guys factorize. But
From this picture,
this is the same picture here.
I'm not understanding. You had these two CFT cuts slightly away from the part which has the gravity.
Yeah, but now it's inside the gravity region.
Why did it go inside?
I'm choosing that. I took it to be that.
Oh, okay. So
This is a different case.
You chose your region to be that way.
Yes,
Okay, I'm sorry.
because it gives you a very nice result. So
Actually, I don't even, sorry to interrupt, please, excuse me. I guess what I do understand is approaching the boundary of the gravity region. I don't understand what it means to locate the cut at some location inside the gravity region. In that there's no covariant way of specifying that, right?
I agree. There's a subtlety like that.
But perhaps you mean it's enough to sort of approach it.
No, you have to be inside. You really have to be inside the ADS2 region, at least a small region inside.
And then how do you specify the path integral in some coordinate invariant way when you say that? I sort of see what you're saying, but it just.
Can you give the distance very small from that point?
The fluctuating metric, you draw null trace or something, is something complicated like that.
Okay, that's something to think about. But the thing that it gives you is very interesting.
Yeah.
It factorizes.
Yeah.
That means the trace rho to the Vn is literally just equal to, these are just, this is just the overlap of the Hartle-Hawking states. To the power of n. So this is just equal to 1. So the entropy is equal to 0. So the entropy of the entire CFT, including the endpoints, is equal to 0. So it tells you that that's the entire system somehow. Right? Yeah. And the last example I wanted to give is related to a question that was asked. Is the following. So let's consider now the case.
Sorry, I didn't, so there was no gravity, you just doing this computation in CFT.
Yeah.
Then of course there would be windings associated to this part.
Yeah, then you would not generate this cut here.
Yeah, what is the generation of the cut? I didn't quite get that.
So the idea is that gravity can connect the different sheets together.
Not overall sound.
Well, you can call, I don't know if you want to call this thing a wormhole. It doesn't look like a wormhole to me. It's like half of this disk or half of this disk connects to this half of this disk.
Through this, as you draw this path, this kind of thing, the path of the Schwarzschild particle that you were talking
So
about.
yeah, so the path of the Schwarzschild particle is clear how it connects the two. But now I'm saying even throughout the bulk of this disk, right? The Schwarzschild particle is just a statement about the boundary of the disk.
It's just an obvious new manifold, right?
Yes.
It's just an obvious new manifold. You make new R's. You have this boundary condition here, this boundary condition, you can sew them together. Just by a disk inside. It's the top of the first guy and the bottom of the second guy joined together to make the same manifold.
And you keep repeating n times.
Yeah, and it's consistent with your boundary conditions.
Yeah.
And so it's the solution.
Exactly. And then you just you get entropy is equal to 0.
And you got disconnected manifold like that.
Yeah, you got n disconnected
After doing this.
after doing this.
How can this be? So one particular probe of the geometry is if I go around one of these points n times, from this point of view there is no special point. From this point of view there is this. If I just pick one of these points, I don't go both of them. Let's say just pick one of them and go around n times, I get somewhere else. But what is this?
No. What do you mean by go around? So here I didn't tell you what the solution is in the bulk. There's gravity. So the claim is that the solution secretly has a branch cut here. That's this picture that I was drawing. The gravity generates this cut for you.
That's what happens dynamically.
Exactly. And so when you go around, it's not.
Allow me to make the following comment that if you didn't have dynamical gravity, then even though your boundary condition naively might have allowed this for, say, the scalar field, it's not the right thing to do because you could have gone around each of the branch cuts individually.
Yes.
You know, but here you can't do that because that in-between region is fluctuating. So all you can do is go around the two together, and for that it's the.
Or the question is, what saddles do you have? So you have different saddles for this. You have different saddles for this gravity region.
Yes.
One of them is the one where you have a cut here, but there's another one where there's no cut.
It's just the obvious solution.
It's just the obvious. All I'm saying is the requirements are also different with and without gravity.
Yeah,
So what is the allowed solution?
The analog in a pure field theory would be just cut the whole of the real line.
Yeah, that's
If you cut the whole of the real line, you get the same solution for pure field theory. And that's obvious, right? The entanglement entropy of the whole vacuum should be 1.
No, that's not a fair question. I mean, the question is, for the field theory with two cuts, what is the trace row to be in, right? And then, you have to connect the n and come back after that.
Mhm.
No doubt.
Even though if you'd gone around both, you might have said,
No doubt.
Yeah,
No doubt.
yeah,
Because in
yeah.
field theory, you can talk about how to go around this guy.
Yeah, that's
Yes,
all I'm
yes,
saying.
yes.
In gravity, you can't.
That's the only
It's amazing.
comment.
That's why this is the analog of just
No,
cutting
but
the whole
with
thing.
gravity you can if you look at saddles, right? And you're saying
A different saddle.
dynamically the dominant one is where the whole thing is cut and goes.
That's right.
Right.
That's right.
But you can't make a contradiction by saying I could have.
Yeah.
If
That's
the
what
other were
yeah.
dominant, then I could say that.
Yeah, but you couldn't
No, but-
before knowing what was wrong.
Yeah.
Yeah.
Of course, yeah.
Yeah. Okay. So let's consider this case, where you have one point in the bath and the other point there. So then the picture here would be. So it's the same thing.
What is this, the analog of the second branch cut is at the boundary?
Sorry. This now is the disconnect is different from this case.
Oh,
So we're done with this case.
we're done with that?
The punchline of this case was that gravity generates a cut
Right.
the entire thing, and then you just get trace row to the n is 1, and the entropy is 0. Okay?
And sorry, just one more comment. Again, the way this is like cutting the whole thing in the field theory is because if you go to the boundary description, it is cutting the whole thing.
Yes, exactly. But I didn't put that in. That came out.
Because in the boundary, there's the bath, and there's the field theory, and there's nothing else.
Yes,
So
exactly.
by going to the right of that, left of that, you have cut everything.
Yes.
No, I completely agree.
Yeah. But you agree that I didn't put that in by hand.
You didn't put that in by hand, but you did the slightly illegal thing that Sandeep.
Yeah, there's possible thing there.
On the border, but the answer is clearly correct.
The illegal thing was to say, I go a little bit in here.
Yeah.
But then Sandeep says you can't specify where you go. But he didn't need to specify where he goes.
Yeah.
As long as he has a point on the boundary.
That's the thing. The real thing is you're going to the left of the field theory.
Yeah, yeah.
Now in that figure, this dot is inside
ah.
or on?
The same. So it's the same idea. It's kind of a little bit inside. And now we have. Let's
So
consider.
I see the second thing is a little bit inside.
Yeah. Now we look at the Schwarzian particle, and so you go inside here, or you go this way
Actually,
there.
I missed this one. Sorry, you got only one?
I'm considering this case.
What is this case?
This is a case where one branch point is in the bath, and the other one hits the boundary. In the same way, so over there, I had two branch points touching the boundary. Now I have one only. Okay? This is like computing the entropy of just one half, or this thing can be very small, very close to that, and so on.
Part of one half, as part of the radiation, but all of
The right black hole, yes, the right boundary. So now let's do that here. So the Schwarzian goes in there, comes out there, it goes in here, and it comes out in the next one, and so on and so forth. So now you need to fill in the bulk geometry, which has this Schwarzian, this winding Schwarzian as its boundary, and that solution will naturally have a branch cut somewhere, or you can think of it as having a branch point somewhere in the bulk, right? So if I go around like this, I come out here, and so on. So the point here is that there's a solution that joins the Schwarzian particle that winds n times.
Sorry, that is not your only criteria, right? That there is a solution. This is the dominant one, is what you're saying.
This is
That's not sufficient. I mean, I could fill it out so many ways.
correct. This is a solution.
Okay, and is dominant one.
Yes, I believe this is going to be the dominant one in this case.
Even in this case, this was the dominant one.
It has to be because it's 0. The entropy was 0 in this case.
Oh, that
Yeah. Here, the statement is that if you work now in the branched cover, you can represent these connected. I don't know how to. So again, when at integer n, you don't really have a branch point. It's a smooth solution. But if you work near n equals 1, but you can still represent it as something that looks like this. So again, gravity, what it does is that it extends the branch cut into the bulk, and it gives you this new branch point.
And the location of the branch point is fixed inside the, or is it?
Yes, it is fixed by the equations of motion, and you can show again that it's equivalent to extremizing the location of this thing.
quantum extremal surface.
Exactly, the
This
quantum.
part of the radiation.
Yes, but take this thing to be very close there. This is just justifying the Engelhardt wall formula, right? So this is how it's derived actually. Well, I mean they propose it, but then Dong and Lukowitz derive it, or prove it, or whatever the word is. Yeah, and yeah, so there you go. Let me see.
Maybe that you have to include just, this is how they stated it, but then derived that you have to include the matter part in the line extending from X to the boundary, to Eustachian,
And extremize the whole thing.
and extremize the whole.
That's right. Yeah.
If you take that picture and bring the points closer and closer to the circle,
Hmm.
what happens to the island inside?
It doesn't move by much.
Doesn't move.
But if you touch the boundaries,
That will then
then you get that exactly.
Is there a way of cutting, not in the t equal to 0 slice, but in a different slice, so that you just pick up a part of the radius and let's say up to some time, not the whole. Is there a way of cutting this in a different manner?
To get what?
If you have the bath
Yes.
space-time, so far you are cutting in a constant time slice.
Yeah. So
And
the idea.
As a function of time, you are looking at the answer.
Yeah. The idea ultimately is that you simply continue the location of this.
Right.
You analytically continue to whatever time you want, and so on.
But you might not like to cut exactly always on the constant time slice.
No.
You could cut a little interval there.
You can do whatever cut you want, but then ultimately, so work on t equals 0 slice, but then continue to whatever your desired Lorentzian time is.
At a constant time slice. Okay.
You can continue.
You make a cut on an interval. Can you make a local statement that locally that is dual to some other local part?
yeah, so I mean, when you compute anything, whatever you want, you always have to include wormholes. But the question is whether those contributions are ever dominant, right? That's the statement.
And sorry, the fact that you extremize in Engelhardt and whatever, or generalized Eutracking, that follows from the equation of motion.
That's right. That's right. That's right. Yeah.
On the other hand, if you take matrix elements, then you might have semi-classical generalization of RT formula for matrix elements in this way.
Yeah, but for matrix elements, I don't see the replicas yet. So here I had to take trace row to the end, so I had different replicas, and then I connected different replicas. But if I'm just considering a single matrix element, it's not entirely clear to me right now.
Very interesting.
Yeah. Yeah, and now, so the fact that different.
So does this tell you something that some particular point on the boundary is dual to a particular point inside? That should tell you something more.
Particular points, I don't know, but we can say that this region is dual to.
No, not region. So instead of doing this calculation, I want to take a small interval on the bar.
Then most likely thing will happen is that it will not care about things here.
No?
No.
Only if you capture the whole entire
Yeah,
relation,
yeah.
right?
That's right. That's right. That's right. The intuitive. Okay, I don't know if this is intuitive, but one reason is that's often given is to say that local observables, simple observables here, cannot probe this non-locality that we're seeing. You need something really, really complicated and so on and so forth.
Because most of it will come from the rest of the bar.
Yeah, exactly.
If you take the point on the bus, so in the bus part, the cut is ending somewhere. If you take it closer and closer to the boundary.
I'm taking this guy
Yeah.
close and close to the boundary.
Take closer and closer to the
Good.
boundary of ADS2.
Good.
Then would it at some point would it stop being the dominant saddle, the one that you're considering?
Yeah, I mean this thing might move a little bit, but that's it.
That moves inside the bulk, but
Yeah. In response to moving this, but I think this will continue to be the dominant saddle. Because ultimately in the limit, as you take this thing to 0,
This is what we have already calculated in the earlier part of the drop, where this was almost near the boundary.
yeah,
and this was
exactly.
the
We know what the answer should be, and it looks something like this.
Yeah, so from here also we should see that there is no change of dominance or anything.
Yeah, you should be able to see that. I haven't done that. Yes?
Cannot model before the phase time.
So in this case, I was doing at t equals 0. This contribution is not the dominant one at t equals 0. But we have this other contribution where there's no island. But now the idea is that you continue these guys to Lorentzian time and see how they evolve. And one will dominate over the other at some point. Yeah.
That's a calculation. This exchange of dominance when you continue to Lorentzian time, so that's a calculation. Or
That's a calculation you need to do. I guess ultimately, yeah, you need to. Yeah, let me see. How would this actually? How would this actually be done? So we're ultimately continuing this quantity.
Yeah.
So yeah, so we're just comparing these different saddles where we continue the exponent in Lorentzian time.
Yeah.
And at some point there's going to be a switch, and this guy's going to win.
So that can be shown.
That yeah, in principle, yes, can be shown.
And that's the Lorentzian calculation.
That's the Lorentzian calculation, yeah. But I guess maybe the question was kind of related to doing this at finite n,
Yeah.
like not n equals 1, n equals 2, 3, and so on, showing they have a saddle for these different n's when you continue this quantity.
Exchange of dominance is just
So
a
for trace
generic
row
form.
to the end.
Yeah, exactly. I worry that some things might become complex or something, but no, I guess it won't be. But I don't know. That's a calculation that we need to do to completely justify this in the time-dependent case.
Would this things go to if this to be compact, right?
Can you say that again?
If you take this into a cylinder,
Yeah?
then same kind of conclusions.
Yeah. Yeah. That's actually all I had with regards to this topic. The other thing that I was going to talk about was something about big black holes and state dependence and so on. But do you guys have any more questions?
Just in your original exchange of dominance story, which I suppose is equivalent to this, I want to understand the scale is better.
Scales.
The time scale is better. So there was a time at which this exchange happened. Could you a little bit indicate how that time came about, please?
Yeah, so first of all, so we have to draw the page curve. You're asking about this time here.
This time, I understand from the page curve.
Yes.
From your saddle calculations, how do you see you get the same?
But it's the same, because what appears here is the entropy that we use to get this picture.
Okay.
That's separate.
Okay, just, you didn't, the ground state entropy, that is S naught played no role.
Um,
And
That's
it's
right.
probably because when you say you're past the page time, you actually sort of built up so much entropy that
Exactly.
doesn't matter.
This thing, well, it's not that. So the value of the Bekenstein-Hawking entropy here has two factors of S naught, right? One from each horizon. But this thing grows linearly in time for all time. So at some point, the entropy will be larger than that.
But is that, so it really, you see the crossover exactly dependent on S naught?
Definitely, yeah. Let me see, actually.
In your
Yes, it does. Yes,
calculation,
yes.
S naught.
I ignored S naughts in my equations. No, that's because I ignored it, because to me, it's just an inconvenience. It doesn't come into the extremization, because it's a constant.
Yeah, it doesn't come in. So all I'm saying is the time scale on which the crossover occurs
Mm-hmm.
doesn't care about S naught there. You know, you have two
No. The location of the quantum extremal surfaces does not care about S naught. But when the minimality condition kicks in to switch which one wins, does depend on S naught.
But the minimality, I thought you were just using phi plus log, etc.
Implicitly inside phi, there's a phi naught. Right? So you agree that phi naught controls the size of this thing, right?
So you say we should add a phi naught there
Should I?
also.
Yeah.
Coming back to these different saddles, my main question will be, is there a situation where two of the contributions are coming almost equal? So to ask that, before I ask that, given n and given the number of wormholes I have, number of joinings I have, what is the order of the action? Is there a non-trivial play between them that I can see? What is the order of the action given the number of wormholes and given time, let's say? What is the order of that action?
So the thing that controls how many, okay. When you have more non-trivial topology, then you need to add extra factors of S naught and also phi's, I guess. So higher topology often is disadvantageous because you keep adding more and more contributions.
Certain limit, let's say you have some
What do you mean certain limits?
G Newton, you have some limit, definitely you have G Newton going to 0, things like that. So in certain limits, certain things are subdominant, but I just wanted to see a play between them. So if you give all the parameters, then we can, is there something more that you can see? Here everything is dominated by one saddle. Is there a doable calculation in which one can see some play between more than one? Maybe a class of thing that you can somehow, okay.
Maybe there is, but it gets more and more complicated with more topology you add. But I gave us the simplest example where there's an interplay between two saddles, the one where there's no island and the one
This is the place that
island. Yeah, and that's really the most relevant thing for these set of lectures.
But the replica diagonal solutions anyway cannot have things like two disks are joined.
That's
the
right.
rest are not.
That's right. But you can have, so the case that I drew this thing,
Yeah, so this.
I can put a hole there.
Ah. Oh, higher topology. Yeah, I see.
Yeah. So there are definitely higher topology surfaces that respect the replica symmetry.
The reason I'm a bit confused about this S0 issue is because, okay, I can't do it in my head, but just to go back to that whole Hayden-Pascal sort of discussion for the extremal case, you think S0 also enters there in those?
So good. In the extremal case, I was ignoring S. I was actually assuming S0 was not there.
I know
Because
you've been
because
writing phi R and so on, yeah.
no, not because of that, but because I wanted the entire state to be pure. So what's S0? I mean, obviously, so if I literally start with the finite temperature case, the entropy between the entire left and the entire right is some thermal piece plus S0. Now if I take T goes to 0, there will still be entanglement, which is given by S0. But I was imagining that's not there.
Anyway, yeah.
But
anyway,
one
should
yeah.
work it out. I mean, it's
Yeah.
something
But even if you add S0, so to remind you, so we had this picture. So the thing that we need to compare is the entropy of this half space versus the entropy of this half space union the island, right? When we have an island, we also have the dilaton at this point, so there's an S0 term. The entropy here is, with the S0, is finite, but it's large because there's an S0. But that's still smaller than the entropy of a half space, because the entropy of a half space is infinite. So even if you put S0, the island is still relevant.
But it will change anyway, a little bit. It will respond a little bit to us.
But what's going to change? The location of the extremal surface won't change,
Just the value.
just the value of the entropy. Yeah. Yeah. Yeah, so the last thing I was saying was,
Sorry, one last. I'm sorry.
and when I was saying that he interrupted, now I'm going to say it again, he interrupted again. So please, go on.
Sorry. This exchange of dominance happens only in Lorentzian time.
That's correct.
In the Euclidean path integral, this is always subdominant.
This particular island in this configuration
Yes,
case,
it's a
yes.
subdominant
Yes.
configuration.
Yes.
But when you take it and continue to Lorentzian time, it suddenly becomes dominant.
Yes.
It's very much like the Hawking page thing. If you have a two-point function.
Okay.
Say again. So there also,
No,
it's like this.
So the Euclidean action gets extended. I mean, even what I mean to say is the value of the action of the two branches in the Hawking page transition, that there's a sharp transition even in Euclidean signature as far as the value of the Euclidean action is concerned.
Yeah. So what I meant was that suppose we were at above the Hawking page temperature and we were computing a two-point function. In the black hole background, the two-point at early times the black hole background wins, but the two-point function decays exponentially. So if you wait, if you wait for a time of order log n squared or whatever, or n squared, you wait for a time of order n squared, then that decay is so big that it overwhelms the change in gain in action for being in the thermal black hole background and now thermal area space. So in Euclidean space, if you're just doing thermodynamics, if you're above the Hawking page temperature, you always think it's the big black hole there. But if you now take that thing and do the right calculation, namely a two-point function, you will find that at a certain time thermal area is very much like that.
Very, very, very good point.
Mm-hmm.
I see. So somehow the Euclidean calculation only alerts you to the various alphas. Then you continue to Lorentzian to see.
Yes.
It's too good.
Mm-hmm.
It's a little like the 163 PS black hole.
You have to do some other contour.
Man, you have to go to complex chemical potential. Why would anyone want to do? But okay.
Okay. Yeah. Okay. Now the thing that I was going to say. No, he didn't interrupt. Okay. Was that this effect of wormholes in the replica calculation is a general thing. It can apply even in higher dimensions. And in fact, modulo this point where so the honest calculation is that for each individual n, you need to find the saddle, and then you continue and goes to 1. So you need to actually show that there are saddles at these other ends. But so even in this case, it's actually hard to compute. We can only do it, well, in the case that we considered, we were able to do it numerically. And good luck doing this in higher dimensions. But you can work near the n equals 1 limit. And you derive this formula, and this is general. You can do this in, I believe you can do this in any number of dimensions.
But typically this kind of thing doesn't work, right? Meaning
This
you
kind of
just,
thing.
If you work at n equals 1, meaning you just give some conical excess and
Yeah.
go towards 2 pi. Because in order, so just even in pure CFT without any gravity, if you want to do this, on n sheets, you would have operators which will be, nth product. The Hilbert space will be n product, the nth tensor product of the original Hilbert space. And that is what you have to continue.
Mm-hmm,
But you'll never see that in this.
Yeah. My point here is not to actually compute the entropy, but just to show that you pick up island contributions. That you need to include things like this, but I'm not saying let's actually compute the entropy, but just show that it has this qualitative form.
I mean, I thought that was, it's not surprising to me. I mean, what you're saying is you are repeating.
I'm repeating Lefkowitz Maldacena. Yeah, yeah.
I'm just sorry, I'm just doing it in my head. Yeah. You're repeating Lefkowitz Maldacena in this situation where you have gravity, say, for some part and not for another, and in general you pick up the matter contribution in the path integral.
Exactly. Exactly.
But in this setup, if one can compute 2-point functions, this 2-point functions on the outside, and then do the path integral the way you are doing, then probably what Siraj was saying, in this 2-point function, Lorentzian signature, we might see some change of dominance with time. Even here, probably one can do the computation.
Maybe.
Maybe you will see more than just ADS.
Sorry, what do you say? Say again.
Earlier comment was about earlier proposal was one, that if you have 2-point functions at finite temperature around black hole background that decays with time, and at late enough times maybe the one that misses the thermal radius. But here if you want to compute some 2-point function, let's say 2 points outside as a function of Lorentzian time, you might do the computation and probably this one will still contribute, and then you will not see probably thermal radius, but you see something better.
But this is in some two-sheeted, some multi-sheeted.
Yeah, I don't know what you mean by that.
This is the
Yeah.
sheet business is the entropy specific.
Exactly.
Right. But there should be for example, in this one-seated picture, effectively give a branch cut. So there should be some way, even if you are doing a quantity calculation, which is the one-seated calculation. So that should see that effect in some sense. I don't know exactly how to say it. But even in thermodynamics, let's say you are calculating the same density matrix, but you can calculate using replicating. Then probably these ones will still come in. to see that even for thermodynamics, these things are coming in.
Replica trick is because you're computing trace rho to the n, right, with the correct boundary.
That's right. That's right.
Right.
That's right.
Right.
So,
But
I mean, if you're computing 2-point function, which is trace rho phi,
Can we
Yeah.
continue this discussion later? Okay. So now I'm going to talk about big black holes. Non-evaporating black holes to address this question of the black hole interior.
Like Papadopoulos, right?
Yes, the punchline is going to be that Papadopoulos and Raju, or rather, I will present, I think, a very sharp contradiction or counterexample to Papadopoulos and Raju. Okay.
I was about to say everything here is completely consistent with a nice smooth interior, and in fact smooth island, etc., no firewalls. And
That's right. That's right. That's right. That's right. Yeah.
Very consistent graph of the river structure.
Okay. So this is going to be in the SYK model. So you guys know what the SYK model is, right? Yes, you do. Right.
Yes.
Okay. So there we have n Majorana fermions, I, which we can represent in terms of n over 2 spins. With the spin operator, S k hat equals 2I psi 2k. So this is sk, 2k minus 1 psi 2k. There's a nice class of states, which is just the eigenstates of the spin operator. So sk hat on states I'm going to call bs, sk bs. So these are just a product state of spins. We learned from this paper of Corcolo Maldacena that if you consider the following states, bs beta, defined as e to the minus beta over 2h times bs. These states look a lot like black holes, right? Very good. And
sorry, can you say, I'm not as familiar with this as I should be. When you say lot like it, you mean some low point correlator?
correct. I'll discuss it right now. So if you look at the, okay, we can represent this in terms of some Euclidean evolution. I mean, that's what this is. Sorry, in terms of a Euclidean path integral, which looks something like this. So we imagine here, we start with the state bs. Then we evolve for e to the minus beta over 2. That prepares a state at t equals 0. And you evolve for the rest of the way. And then you end up with bs here again. Okay? So this is supposed to, so this is just the overlap bs, bs. And now we can choose to insert operators here. That's like putting operators here. Okay?
What is normalization?
Let's ignore the normalization. It's not important. Say we just for the sake of time. I'm ignoring subtleties or minor issues like that. Say we compute the 2-point function psi 1 at some time t1, psi 2 at psi 1 again at some time t2. Okay? The result of Corcolo Maldacena is that this is equal to the 2-point function in the thermal state. So this is the thermal circle, psi 1, t1, psi 1, t2, for all times. So you can move this around. So it kind of tells you that the space-time here is in some sense. So if you fill this in, if you fill in the ADS2 bulk, it looks like just the usual ADS2 space. So the geometry here inside, you can think of it, it looks a lot like the eternal black hole geometry. But if you compute not a correlation function of psi 1, psi 1, but rather psi 1, psi 2, then you get something else. So for psi 1, psi 1, it's just the usual answer, whatever the 2-point function is in the thermal state. But for psi 1, psi 2, it looks like there's a source here at this point in particular. And the source is just psi 1, at least for this case, it's psi 1 at 0, psi 2 at 0. So ultimately, this thing is just, it's like a 4-point function. Psi 1 at t1, psi 2 at t2, and psi 1 at 0, and psi 2 at 0. Okay? In the thermal state. So this tells you that the Lorentzian picture is the following. You can take a slice, a t equals 0 slice of that space-time, and then continue. So you take this slice here, and it would continue to the following thing. At this point, there's something, you don't know what it is exactly, so let's just cut away the space-time and the causal future of this point. Okay? Let's evolve also backwards in time. Let's continue this thing in Lorentzian space in the past. So it gives you something that looks like this.
Sorry, this was because of the source for side 2, this cutting off business?
Yes. Well, yeah. So exactly, because of the source. So there's something funny going on here, and so we don't want to make any statements about what it looks like in this region. Maldacena, so Cook and Maldacena like to call this like to say that there's possibly an end of the world brain or something. Okay? And yeah, so now if I compute Lorentzian correlators, psi1 and psi1, I only feel the exterior of this black hole, right? But if I compute psi1, psi2, then there's a source here. So it looks like a 4-point function in this way. Okay, good.
So in the first picture, when we did in the just psi 1, it goes, why did you cut off the, I didn't get, why did you cut off? In that case, I'll get the full black hole or?
Why did I cut off the region here?
Yeah.
So we agree that from this picture, there's something here, right? I don't know what this thing is. I don't know what its dual is in the bulk. And so I'm just cutting out this part of the space-time, because I don't know what to continue with too. Okay? There's something here. Yeah. That's how I'm thinking about it.
Such's question is that if you, in this cutoff diagram, instead of psi 1, psi 2, your insertions are psi 1 and psi 1. Then you don't need to cut off, right? Then it's the usual eternal.
No, but you're trying to make a statement about what the space-time is independent of which correlation function you're computing.
Right. So then the point is that this cutoff in the geometry probably does not matter when it's psi 1, psi 1.
Yes, exactly.
For example, if you draw some correlation geodesic or something.
Yeah, exactly. That's the statement is that So in the geodesic in the geodesic approximation, it's just some geodesic that does that. Well, this is not a geodesic, but it's a geodesic there, I guess. I think that the statement is that this 2-point function is like a response function where psi1 injects something and psi2 just measures that thing. So it only cares about the outside of the black hole. That's one way to think about it. But if you compute psi1, psi2, then you pick up a piece. It's the quantum state of the wave function of these fermions in the bulk somehow are influenced by a source there. That's one way to think about it. And it's only these off-diagonal correlation functions that pick it up. Okay?
And I'm sorry.
So it looks like time order. Okay, good, sorry.
Time order.
So what I'm trying to say is that the 4-point function that you are getting in this case, is it going to be out of time order or time order? If I allow you to analytically continue without crossing any branch cut.
It doesn't. I mean, you can pick whichever correlation function you want to compute. Time ordered, out of time ordered.
But the one that you have given.
Yeah.
Which one would it compute? Would it compute time order?
It doesn't matter. So I mean, I didn't tell you what this thing is, so just put all of this here and just say that it's radial ordered or time time ordered. Let's say. But it doesn't matter. It doesn't matter. It doesn't matter.
But Euclidean insertions fixes it, right? Euclidean
Yeah.
insertions fixes it, which order you are computing. So you have drawn the insertions. Okay.
I'm just saying in Lorentzian space you can choose to compute whatever you want.
Okay.
Obviously, ordering in Euclidean space is fixed because otherwise you'll have infinite answers. But in Lorentzian space you can choose whichever ordering you want.
But Lorentzian space that is determined
By the
insertion.
Yes. By the Euclidean time ordering. I agree.
And I'm sorry, you should go. And this is just a statement of my ignorance of SYK and all. But besides psi1, psi2, and psi1, psi1, what about something else?
Yeah. So compute psi 3, psi 4.
Okay, those are probably similar.
Similar. Compute psi 3, psi 5.
And there's nothing. Psi1 doesn't connect to it.
Exactly. Psi 3, psi 5. That's going to be small.
So those guys are also.
Yes, they're all small. Okay, but so this is true for any S I pick here. So I can start with any spin eigenstate and evolve it by this much, and I get one of these candidate states. So you can think of that in this picture as, in some sense, sort of the microstate of this object. In some sense. Okay. There's another way of preparing these states, which is the following, which is to start with the thermal field double. It's sort of suggestive from this picture. So we know how to write this as e to the minus beta h, let's say r. You sum over, so usually we sum over the energy eigenstate basis, left, right. But there's another basis we can use, which are these spin eigenstate basis. Okay, so I can write this as sum s, let me just write it here, s bs bs star, by that I mean the CPT conjugate.
Yeah.
Okay? Okay, so we have something like this. This means that the state bs beta of the right is simply equal to bs star left beta left right. Is that clear?
Beta was thermophile double to begin with. Initially, what did you have for beta? Thermophile double.
Yeah. Beta is a thermophile double, but I'm writing it in terms of this spin eigenstate basis. Okay, and so then I can prepare these states by simply projecting with this bs star. Very good. Yes, thank you. And what, sorry?
HL plus HR.
No, just HR.
There's also some factor of beta HR over 2 hanging around, right? Just from going from that equation to this one. That is, if I take inner,
No,
if I
so
take the inner product of bs star in that sum.
you just mean normalization?
Yeah.
I'm
that's
ignoring
what-
normalizations.
Yeah.
They will not come back to bite me, I promise you.
What is the normalization operator, right? HR is an operator that acts on this.
Yeah?
So when it goes through BS, is it the
This
number
one.
or more than that?
No, he's just saying there'll be he could have written that as HL.
That's right, I
He could have
could.
written that as HL and absorbed it in that inner product of
You are
BS
taking,
star.
right. One of them, L and R, okay?
Yeah,
I'm sorry, you can always take one of them.
Okay. So now, let's consider the following thing. So this observation I claim is very important. So say we start with the eternal black hole. So I'm going to claim this without proof, that you can start with the thermophile double, act with the unitary transformation, say on the left, okay, which creates a particle somewhere here. Okay, so it's deep in the bulk here. Then project in this way. I claim that this prepares the following state. I claim that the projection keeps this particle where it is. Okay? And and you can check this by doing the same set of tricks, by computing the correlation functions of these psi1, psi2s, etc. in this state, and then showing that it's equal to computing them in this state, with the possible inclusion of a source here. Okay.
But you are going to use this state to compute things on the right side only?
Yeah. So now this is a state on the right only,
Right.
and that's so I'm going to do that.
Compute things only on the right, but there is a particle on the left part.
Exactly. But now we could have, so you could have started with the state without that particle. So that's,
But in psi1, psi2 computation, this will affect because this might have a shock. This left
Yeah, exactly.
might have a shock. Then this computation, psi1, psi2 computation,
Yeah,
in this state
will get affected.
affected.
Exactly. Well, it'll get affected in exactly the same way as computing it in the thermal state.
Mhm.
This thing should be related to the state without without this particle via some unitary v on the right. Okay, such a v exists that takes this state to this state. All good?
Let me just, process that. You're saying, look, you have two states as far as the right-hand side are concerned.
One
This
without a
one
particle and one with a particle, so I can construct a unitary.
Not even unique, I mean, there can be many.
Yes, yes,
Okay,
yes.
good.
But, go on.
Yeah, yeah. That is basic. This is Papadodi Raju's attempt, right?
Exactly. So
Construct.
to find this VR is a statement about finding the dictionary for the black hole interior. Okay? Now I claim that in this model, you can prove that VR cannot be a linear operator. Okay, you can prove it. As in, by VR, I mean the operator that creates the particle behind the black hole horizon for the different microstates parameterized by S cannot be a linear operator.
Linear in what?
But I mean, I mean that for different S, you need a different VR.
That's also what they say, right?
I agree.
Okay,
So far we're fine.
Okay.
So far we're fine. Let me prove this for you. So suppose that there's a VR that works for all BS states, right? So the statement is that this happens. You start with this, with some S microstate of the brain, act with V, and you get this for any S. Okay, so VR, let me prove this very quickly. So suppose that such a thing exists.
So you want to arrive at a contradiction.
I'm going to arrive at a contradiction.
I'm too embarrassed to ask my remedial question about state dependence.
Okay?
Go ahead.
Okay. The next, so start with the statement. I feel like a middle school teacher or something. Would you like to share with the class?
I'm responsible.
That's what usually happens, though, right? Pick the other person.
No intelligent person. Okay, look, I mean, let me ask the question, but
Please.
you all can postpone it. I thought what Surat and Kyriakos were saying was that you could reconstruct the interior and states in the interior by using one side as well as the Hawking radiation or both sides.
I'll get there.
And here you have only one side.
Yes,
and
yes.
I'm confused about
I'll get there. I'll get there.
Okay,
I'll get
all right,
there.
so
I'll get there.
I thought it was too dumb to ask.
No. I'll get there. I'll get there. I'll get there. Okay, so let's start with this statement, and I claim I'm going to arrive at a contradiction. Consider multiplying both sides by the ket on the left. So equals all good so far? So I just multiply by the ket bs star. Now sum over s. You sum over s on this guy. That just gives you a 1. Sum over s here gives you a 1. So you find that VR acting on the thermal field double is equal to UL acting on the thermal field double. Right? So this means that, so these are both unitaries, we claimed. Trace over the right, On this side, if you trace over the right, you'll get the thermal density matrix on the left. Here, if you trace over the right, you'll get UL acting on the thermal density matrix on the left. Is that clear? This is a contradiction. Unless U is trivial. But we said U is not trivial. It created a particle here. The left density matrix is sensitive to this particle. So state dependence is a thing. Okay? So the resolution is that this VR secretly has an S superscript or whatever, or dependence.
When you did that sum over S, that was a bit fast, right? In that
Then the
No.
unity will not come out.
Yeah. So now if it depends on S, then when you sum over S, this set of steps will not are not valid. Okay, good. So it's nice that we found in a sort of an explicit example which realizes, I think, state dependence. And so I think it's a good testing ground for current ideas like Papadodimas and Raju. But I claim that their construction fails in this case. So let me quickly review what PR say. So what they say is given state psi such that all sort of external simple operators have thermalized. By thermalized means that it's given by this it's equal to the correlation function in the thermal state up to some accuracy. Let me not quibble about how accurate this needs to be for now. Then there exists interior operators, or tilde, such that the horizon is smooth, right? So the idea such that horizon is smooth. And the idea is that they mirror the operators outside of the black hole but near the horizon to operators behind the black hole and near the horizon. And so it's just a statement that these correlation functions, O in, O exterior, are really equal to, again, e to the minus beta h, O in, O exterior. Okay? So this is their construction. Okay. Now,
sorry, but I thought the construction
Well,
was that then O in tilde can be written.
yeah, the construction, I think this is good. This is not, this is the claim that they can construct O in tilde ins that satisfy these properties, and therefore they look like interior operators of a black hole. Okay. But there are certain black hole microstates. Okay, well, first of all, we can say, does this apply to these black holes? So these black holes have smooth horizons. Does their construction work here? The answer is no, because these are not typical black holes. These have not thermalized. There are simple observables outside, which have not thermalized. In particular, these psi1, psi2 correlation functions. Question is, can you make those guys small? The answer is yes. Consider starting with a thermal field double, then acting on it on the left with a series of out-of-time ordered shock waves. This thing is going to give a long wormhole with a bunch of shock waves. Good? I claim that this thing still has
There will be one more kind of structure. Is it all not joined, right? There is a path.
see that again?
Even if you have acted with all these shock waves,
Yes?
the geometry from the left to the right, is it like a path in between which is like traversable?
No, it's not. What do you mean by traversable? I mean,
You have to keep track of all the change of shocks. There is no path which is traversable now.
what do you mean by traversable?
Okay, so what do you mean by, let's say, wormhole? Like that there is a path through which you can travel.
Yeah, well, you can't actually travel, but there's a geometry that connects this entire region, if that's what you mean.
You go ahead, but I'm not because when the shocks are going in,
Yeah?
they might they can change the location of the horizon. If if they are early enough. So I don't know how early these are.
Yeah, the horizon is here. There's a new horizon outside
Not the
here.
new Penrose diagram.
I understand the new Penrose diagram, but it depends on how early these insertions are. There is a way of, you know.
Let's pick them as scrambling time. I go evolve scrambling time, then 2 scrambling times down, then up and down like that. That's sufficient for this.
Yeah, so they are like, or insertions are early enough that it is order scrambling time.
Yeah, so at least a scrambling time, because I want to be able to, that's what you need for the wormhole to actually become long. Okay? Good. I claim,
Sorry, I haven't fully understood that diagram. So
This
the
diagram?
diagram is in JT gravity?
yes, in JT gravity.
Okay.
It's just a so in JT gravity, it's a statement that, so here's one boundary particle, this is the other boundary particle. If you add shocks up and down, what's going to happen is that you're going to make this thing very small. Like that. And this is like the long wormhole. Okay?
There is a unitarity bound in operation.
Yeah, that's true. And back was also clean.
Oh,
Okay.
okay.
I'm almost done. Okay?
Yeah.
The claim is that if I project on this state with this BSL, then I'll get a long guy like that with the same shock waves. Okay? And this is something you can check. Okay? So we've prepared black holes with very long throats. I can put in, a very large number of these shock waves.
Check meaning that you put it again the flip invariant operator.
Exactly,
and,
exactly.
See that they're equal.
Exactly. You need to assume that these WLs are also flip invariant, which it's fine. You can do that. Yeah.
You have a wormhole or not in this part?
So this is a wormhole. This is a pure black hole with a long throat.
In the previous one, you did have one.
Yeah, there are 2 exteriors.
Why do
And
you need that?
they're joined. You can have you can even have a geodesic in between which does not go inside any one of the horizons.
Time-like or space-like?
The geodesic would be like the space-like.
Space-like?
I mean,
Not through the bipartisan ones.
a geodesic. I suspect so. I don't see why not.
So if it is, then I will not want.
Yeah. There's some path that they go from one side to the other.
But that part does not go through any one of the horizons.
Does not go through.
Any one of the interiors. Does it go?
I mean, this is the interior here.
I mean, just
How can you go from one exterior to the other without going through the interior?
Maybe I misunderstood. You go on.
Okay. So now we have these pure state black holes, but I claim that this black hole, from the simple observables perspective on the right, looks like a typical state. It looks like it's thermalized. The troublesome correlators are now going to be, let me call this thing.
Because the source is too far away.
Exactly, that's why. So if you can compute psi 1, psi 2, this is going to be small. It's going to go as e to the minus number of shocks because the source is now really far away. Okay? I should say that all my statements are up to some correction, which goes as order n to the minus q, where q is the SYKQ, the number of fermions in the Hamiltonian interaction.
So that's the measure of the non-flip invariance of the
Exactly. But let me work with Q very large.
Okay.
All these statements still apply. So we have a microstate that looks typical. It satisfies this condition of Papadodimas and Raju, but that construction is completely oblivious, or the exterior, the correlation functions outside are completely oblivious to whether there's a shock wave right here. Right? In the way I constructed, this WL can have a shock wave there.
But can I compute the following correlator? Take one operator on the right boundary and one on the. Is there anything on the left?
Are we talking about this? Are we talking about this case or this case?
Let's have to begin with in this case.
In this case, there's a left boundary, so I can compute left-right correlators. Sure.
Left, right, and you will surely see. Then you will surely see the effect of the effect of all the softwares that went in. You will surely see.
I agree. Yes.
Now here you don't have any left. You don't have anything left on the left. Is there any boundary on the left where I can put an operator?
No.
It's totally.
There's nothing here. But you can compute the psi1, psi2 correlation function. And that does depend on all of this structure, but nevertheless it's going to be very, very small.
Right, and bulk boundary propagators don't count, presumably. They don't count because they are not right.
Well, I mean, there are observables that correspond. If you have the dictionary for the interior, there are operators here, and you can compute the correlation functions with things outside, and you can deduce that there's a shock wave. I mean, there is a dictionary that can tell you everything about the state. But that's not the question that we're addressing now. The question that we're addressing is, can one write down a state or a set of states that satisfies the Papadonimus and Raju criterion, but nevertheless has a firewall behind the horizon? And I think this is a very clear example of that. So
explain that. How does it have a firewall?
So I just mean that it has a shock wave behind the horizon. They claim that if all the operators are thermalized, then you can construct these interior operators such that the region near the horizon is smooth. There's nothing there. There's no shock wave. It's completely vacuum.
Because of that factor,
because of this.
That's the thing between Riddler and.
Exactly. But here I've explicitly put in a shock wave just behind the horizon, and these correlation functions don't see that. These simple correlation functions that they want to use to be able to get the answer. Yeah.
One sec, let me just make sure I understand the chain of logic. So their point was that if you had this O tilde interior, and then if you were at late time, then their correlators would be given through the thermal ensemble like this.
Yeah.
That just comes out from the black hole geometry.
Yeah.
And then that helped them reconstruct O in tilde in terms of
Yeah.
And here you're saying that.
So here, I was going to say something about what you just said.
Okay.
So here, even at late times, presumably these shock waves would fall into the horizon, into the singularity.
Okay.
Like it would crash into the singularity, and then yes, you would have a horizon region, like a smooth horizon region or something. Sure, but that's not the point of the argument. The point of the argument is I can make their arguments at t equals 0 here. So even at t equals 0, everything is thermalized from the exterior's perspective.
So you're saying even though this last equation is true, it doesn't mean that the horizon is smooth. The horizon is not smooth in your case.
Yeah. So
still the last equation is true.
it's true because these O tildes do not correspond to what they thought they correspond to, right? So I want to understand. So
meaning that suppose you have the simple operators like the flavor invariant operators
outside.
Calculated on that right boundary. And you find that these two geometries give you the same result.
Yes.
Okay, which would mean that
No, that's not associated to this.
No, sorry. So take me through the chain of argument.
Okay.
Why there?
So the first chain of the line of reasoning was just to convince you that if I start with this state and I project, I get this state.
Good.
So we're good with that?
Yes.
This state has a shock wave just behind the horizon.
Good.
So we would not categorize this state as having a smooth horizon. Because if I fall in, I would hit the shock wave.
Okay.
Good? Okay. Now the question is there a diagnostic from the outside that can tell me whether there's a shock wave there or not? Okay? In principle, there is. If you know the dictionary entirely, so you know the dictionary for the interior, that will tell you if there's a shock wave. Papadonimus and Raju claim that they have a dictionary, which is the construction of these O tildes. Right? But the O tildes tell you that the horizon is always smooth. So they would not tell me that there's a shock wave there. That's the problem.
Sorry, I just want to ask you this. That dictionary is state dependent, right?
Yes.
And is it the case that even even for this state where you have a shock wave on the inside? Let me put it the following way, and I
Please.
could be ignorant. You know, let's take the thermophile double situation.
Yes.
And have a shock wave
Good.
just hugging the horizon from the other side,
Sure.
because something started from the right boundary,
Good.
right?
Left boundary.
There, what would Papa Dimas and Raju say? What would the story be there, and how is it different for your case here?
So in that case, there is an exterior. So that shock wave is on the left exterior, correct, or the right exterior, whichever.
I was making it.
Choose one.
On the, it's inside the right horizon.
But if you continue it backwards, it becomes a left exterior thing.
Yes.
What does that mean, left exterior?
It's a particle on the left one.
Yes, yes. Oh, left exterior, yes.
Right?
That's
Right.
right.
So here you have a simple. So here there are exterior operators on the left that are sensitive to the presence of that shock wave. So this state does not satisfy this condition.
But there's no analog of that here.
Exactly.
If you have an operator late enough, so why do you have the whole part is inside the horizon? This is the part I'm finding most.
Why do I have what?
Say,
All?
can I just draw one picture?
Please.
Quickly draw.
So this brings me to this thing that you don't have the analog of Hawking radiation in it.
No, but that's not important.
In this picture, you can have softwares where you have things like this, or this is not the horizon. This part is not at all the horizon. So this is not.
What are these things you're drawing?
You can act with operators here early enough to create a geometry which has something like that. But your picture somehow has everything inside the horizon. This is what I'm not.
I don't know what the thing you drew is. What are these lines that you're drawing?
Right. So here, this one, everything that you had, these are the horizons. These are the parts inside the horizon.
Okay. No. Sorry. Wait, but what are these lines?
So you started with a black hole and you are
Yes.
hitting the left boundary with one by one
Shockwaves. Yes.
shockwaves, which
Yes.
are early enough. So they can change the geometry.
On the left. Yes.
On the left, they can change the geometry.
Yes.
They can even push the location of the horizon up and down if they are early enough.
Yeah. But sure. Yes.
Right. So it could be that the geometry that you are creating has structure like this. So these are the parts which are like, these are not connected. These two parts are not connected.
Okay. But why is that important?
Right. So if you have started with some geometry which is like this and created this black hole, then you will have external operators here. I'm not understanding why you never had an external operator. Why is it that everything here is inside the horizon? How have you constructed? I'm not understanding this.
Sorry. This is so I started with this black hole. You agree that if I act with unitaries on the left, I will not affect this part of the geometry, right?
Absolutely. Yes.
The only thing that can happen is that I'll put things here and I can possibly make this thing longer. That's all I'm saying.
But what is the guarantee that when you act with the unitary at so early time, that you will not open up the horizon?
Open up this horizon?
Yeah.
You can't. You'll reach a contradiction. Because I'm only acting with the left. I should not be able to communicate to the right.
Oh, maybe the one I am writing that also has right side of actions.
Maybe.
That
But
would be the one then.
I'm acting only with the left guys.
Maybe I have softwares on the right also.
Yeah.
But then, I see, okay, it's very interesting, but then if you had managed to probe your psi1, psi2 observable, even though it's suppressed, you would have seen the shock.
That's right. You would see some sign of the shock wave. But I can add a lot of shock waves. Whatever order n shock waves.
Okay, and, all right, you should go on and.
This is all I had. Should we try to end now?
I think maybe, and then.
Okay. Maybe I guess one last comment. Thanks a lot for the invitation, and this has been a lot of fun. I don't think I've ever had this much fun delivering lectures before. And I look forward to many times in the future.
Come back.
Yeah,
Great.